Hello, good people. Welcome to video number 2. We are looking at some rational function integrands. The inside of the integral is like a fraction. How do we get around that? I noticed that in example number 2, and I'm just going to start here. I noticed that the exponent, the biggest exponent, the degree on the numerator is 4. The biggest exponent, the denominator, is 1. So I have a top-heavy situation. It might be a good idea to do some division. And that's exactly what we're going to do. So I'm going to take the denominator, and I'm going to divide that into my numerator. And I'm going to play this game of what times what gives me what. So here's how we start. I'm always using this as what I'm going to multiply by. 3x times something gives me this first term. What times 3x will give me 6x to the fourth? And I believe that would be 2x to the third. Let me not use this color. Let me use this color, 2x to the third, right? 2 times 3 is 6, x to the third times x is x to the fourth. But if I multiply this times that, and I get 6x to the fourth, I also have to multiply this times the minus 5, and I'm going to get 10 minus 10x to the third. Great, I need to subtract. The whole purpose of figuring out what times what gives me this first term is so that I can subtract it out. And I am going to subtract it out. Dang, that's gone. But here, I'm left with 3x to the third, plus everything else that was there. And so I continue my quest here. What times 3x will give me 3x to the third power? Well, that would be x squared. X squared times 3x would give me 3x squared. So I write that down. And then I also multiply x squared times minus 5. That's minus 5x squared. Oh, but now I need to subtract. So it's going to change the signs here and change the signs here. Why do we do that? So that this can be gone, and then this is what's left over. And so that's going to give me 6x squared plus 2x. And I keep going. What times 3x will give me that? That's going to be 2x. 2x times 3x, that's 6x squared. And then 2x minus 5, that's minus 10x. Oh, but we have to subtract, so minus, and then this is going to change signs. And so now I'm left with 12x. And I can do one more. 3x times what will give me 12x, and that's going to be plus 4. That will give me 12x, and this will give me minus 20. And now I can subtract, and I have 20 left over. This is my remainder. And so I'm going to add it on, and I'm going to add it on as plus 20 out of 3x minus 5. Great. The whole purpose of doing that long division was so that we could take the antiderivative. So now I'm ready to take the antiderivative of 2x to the third plus x to the second plus 2x plus 4 plus 20 over 3x minus 5 dx. I'm going to start taking the antiderivative. I can just do the reverse power rule. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. The antiderivative of a constant is the constant times x. And then here, once again, this last part, whenever, and here's a hint, whenever the derivative of the denominator is in the numerator, or I can somehow make it into the numerator, then I can use a natural log antiderivative. And just to show you here what I mean, if I take out the 20, I'm left with 1 over 3x minus 5 dx. If I say u equal to 3x minus 5, that means du is equal to 3 dx. I don't have a 3 dx, so let me multiply this by 3. But if I multiply 1 times 3, I got to compensate it by dividing by 3 in the on the outside of the integral. So now this is going to leave me with 20 thirds, the antiderivative of 1 over u du. What happened to the 3? Well, the 3 dx becomes du, and then the 3x minus 5 becomes u. And now I see that, oh, this is the natural log of the absolute value of u. And then I can put this whole thing back in there. So that my antiderivative, my last piece here, is plus 20 thirds natural log of the absolute value of 3x minus 5 plus c. This is the antiderivative of the original rational function that we started with on number 2. The moral of the story is long division, as lengthy as it is, can help us take a rational function that looks complicated and break it up into little pieces so that we can find the antiderivative a lot quicker. We invest time at the beginning simplifying it so that at the end, when we take the antiderivative, it's a lot faster.